Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about Gaussian discriminant analysis, which is a popular technique for classification based on Gaussian mixture models. We're going to apply this technique to perform diagnosis of Alzheimer's disease from features that are extracted from magnetic resonance imaging scans. Let's get to it. So we're going to talk about Gaussian discriminant analysis. Our goal is to explain how to use Gaussian mixture models to perform classification. And as a motivating example, we're going to consider the diagnosis of Alzheimer's disease from magnetic resonance imaging scans. To give a little bit of context, Alzheimer's disease is a devastating neurodegenerative disease which causes between 60 and 70% of the cases of dementia. You can diagnose it very well using positron emission tomography, but this medical imaging modality is invasive and very costly. It would therefore be very interesting to use magnetic resonance imaging, which is non-invasive and less costly. Okay, so our goal here is to diagnose Alzheimer's using features extracted from magnetic resonance imaging scans. Here is the magnetic resonance imaging scan of cognitively normal patients. So this patient does not have Alzheimer's. We're seeing different views. Each of these images is a different view from a 3D MRI scan. And if you compare this to the corresponding views for a patient that has Alzheimer's, what we observe is that the gray and white matter in the brain, like the different brain regions, atrophy, they shrink in the Alzheimer's patient, which is why you see the ventricles here, this space that there is in between, become larger for the Alzheimer's patient. The reason is that the different brain regions are atrophying, they're shrinking. And this is the kind of structure that can be seen in the MRI scan and which we can perhaps exploit to diagnose Alzheimer's from this data. So let's talk about the problem of classification in general. In classification, we have data that are structured in the following way. The first element in this tuple are the features, which we represent as a d-dimensional vector. So here there are d features. Here, in our example, we're going to have two features extracted from the MRI scan. And the second element of the tuple would be the label that indicates the class. In classification, you have a fixed number of classes that each data point can belong to. In our case, we're going to have Alzheimer's and healthy. So here, we would have the features extracted from the MRI. As you will see, it's going to be two features. And this label would indicate whether each of the patients has Alzheimer's or not, or is healthy. Our goal is to use this data to fit a model which can then be used to assign a class to a new feature vector. We're going to address this problem via probabilistic modeling. We're going to model the features as a random vector x and the class as a random variable y. Notice that the features are a random vector because they have multiple entries. For the class, we can just get away with a single random variable that indicates, in our example, whether the patient is healthy or has Alzheimer's. So we have a new data vector x, and we know the joint distribution of the features and the random variable, then a very reasonable way of estimating the class is just saying, well, among all of the possible classes, let's see that we have C classes here, which of them maximizes the probability of that class given the observed x. Okay, so here you would plug in the observed value of the features. You would take a look at the conditional probability of each of the classes given those features, and you just choose the one that is the most likely. And this is optimal from the point of view of probability of error. Perhaps I will do a separate video to actually prove that. It's not very difficult to prove. So it seems that this problem is quite easy. Okay, like it seems that classification is pretty easy. You just model the features and the class as a random vector, as a random variable. You learn the conditional probability of the class given the features. You maximize it given your observed features, and you're done. You have the best estimate for the class. So is this easy? You might want to pause the video and think a little bit why this problem might not be completely trivial. And the solution, as often is the case in data analysis, is the curse of dimensionality. Well, not the solution, but the reason why classification is not easy. Because unless the number of features, the entries of this random vector, is very small, it is going to be completely impossible to estimate the conditional probability of each of the classes given every possible value of the features that you might observe. We have talked about this in other videos, but you can imagine here, if you have just binary features that can be equal to 1 or 0, and you have m of them, the possible number of features is 2 to the m. It explodes exponentially as we increase the number of features. So even if you have just 100 features, which is by no means rare in real applications, then it's just going to be impossible to estimate 2 to the 100 conditional PMFs from your training data. You're never going to have enough training data. When you observe test features that you want to classify, you won't have that precise configuration in your training set. And that's the main challenge of classification and why classification is not trivial. We already discussed this when we introduced naive Bayes. And in that case, the way we overcame this curse of dimensionality was by assuming conditional independence of the features given the class. That's a naive assumption, and that's why this is called naive Bayes, but it often works quite well. Here we're going to take a different route. What we're going to do is we're going to use a parametric model to represent the distribution of the features given the class, and then we're going to apply essentially the same argument or the same procedure that we applied with naive Bayes, where we're going to use one of the variants of Bayes' theorem to then derive the probability of the class given the features. So here our assumption is going to be that we can model the distribution of the features given the class using a parametric distribution that depends on the class. In order to make this clearer, let's look at a super simple example where we want to classify people according to their height and determine whether they're women or men. Okay, so here we have a single feature. Notice that I'm going to be using examples with 1 or 2 features, which are not particularly interesting in reality, so that we can actually visualize everything and understand what is going on. In practice, you would then go and apply this methodology to a larger number of features, which will enable you to perform better classification. Okay, so here's our data. We have some women. This is the histogram of their heights. And we have some men. This is the histogram of their heights. We know who are the women and who are the men. And now we want to develop a model that is able to classify people just using their height, discriminating between women and men. And the way we go about this, sometimes I forget what I've written in a slide, so let's see what is in this slide. We're going to model the height as a continuous random variable h, and the sex as a discrete random variable s. Okay, and we do have to establish notation. I was just getting too excited and getting ahead of myself. And now our assumption is that the conditional distribution of the height of h given a fixed value of the sex is Gaussian with parameters that depend on the sex. So essentially, we're going to take the men and the women and model them separately as Gaussian random vectors, where the parameters of the Gaussian random vector depends on the class. They depend on the sex. So just as a reminder, we have some videos on Gaussian random vectors. So if you don't remember this, just go and take a look. But basically, Gaussian random vectors are the most popular parametric model for continuous variables. The joint PDF of a Gaussian random vector with the entries looks like that. And perhaps the most important part to remind you of is that there's two parameters. One is the mean, represented by mu here. It's a d-dimensional vector. It tells you where the Gaussian random vector is centered. And there's another parameter, which is the covariance matrix of the random vector. And basically that tells you how elongated the joint PDF of the Gaussian random vector is in different directions. Okay, we're going to see some pictures in a moment. And that's what you estimate from data in order to fit a Gaussian random vector. Okay, great. So if you remember, when you do that, when you fit a Gaussian random vector, the way you fit the mean parameter is actually very intuitive. You just compute the average of all your data points, and that intuitively gives you the center of the parametric distribution. In order to estimate the covariance matrix parameter, you essentially compute the sample covariance matrix. There's a separate video on covariance matrices and sample covariance matrices if you want to take a look. But essentially here you're taking outer products of each of the data points minus the mean, okay? And this you're going to multiply with each of the data points minus its mean transpose. So this is going to give you a matrix that is going to be d by d. And then you're going to sum all of these matrices and divide by the number of data points. Okay, that's going to give you the covariance matrix parameter for the Gaussian random vector. So now remember, our strategy here in order to bypass the curse of dimensionality is to fit a parametric model of the features given the class, which is going to be different for each of the possible values of the class. So for woman, we fit a Gaussian model to the data. We have just one feature. So instead of a Gaussian random vector, it's a Gaussian random variable. And how do we estimate the mean and the covariance matrix parameter? Well, the mean, we just average all the data. It's going to be the average height. And in this case, the standard deviation parameter, because we have one feature, we don't have a covariance matrix parameter, we have a variance parameter. The square root of that is the standard deviation parameter. It's just the sample standard deviation of the data, which happens to be 6.4 centimeters. The average height among these women is 163 centimeters. You can see that the Gaussian model fits the data very well. You might be wondering why we need a Gaussian model in this case. We could just use kernel density estimation or even a histogram, and that's true. However, if we had more features, not only height, but maybe like 20 features, then the histogram and kernel density estimation, because of the curse of dimensionality, would be extremely noisy. And that's the reason why you would apply a Gaussian parametric model. So it's good to bear that in mind. However, we're going to use this example because it's easier to visualize everything. And that's why we're using examples with just one feature and later on with two features. Okay, so we have our model of the features given the class for women. What do we do for men? Exactly the same, except now we're going to have different parameters, okay? We're going to have a different mean, which is taller in this case, 176 centimeters, and a standard deviation that is actually kind of similar, 6.9 centimeters. Okay, so we have a parametric model given the women, parametric model given men. We also need the marginal distribution of the sex, because now we're going to use essentially Bayes' theorem to derive the conditional probability of the class given the features. Since we have around 2,000 women and 4,000 men, basically the probability of women is around 1/3 and the probability of man is about 2/3. Okay? Now we have modeled height as a Gaussian mixture model. We have talked much more about this in a separate video on discrete and continuous random variables, but basically, if you want the marginal distribution of height, you take the conditional PDF, the marginal PDF of height. You take the conditional PDF given woman, you weight it by the probability of woman, and you add the conditional PDF given man, and you weight it by the probability of man. And then we get a nice Gaussian mixture model that models our data very well. And we saw in a separate video that it models it much better than a single Gaussian. Okay, but here we didn't really want to model height. What we want to do is to classify. In order to classify, we need the probability of the sex given height. How do we get that? Well, we're going to apply Bayes' theorem, which is essentially just an application of the chain rule for discrete and continuous random variables. So remember that if I take the marginal of the continuous random variable and I multiply it by the conditional PMF of the discrete random variable given the continuous random variable, that's exactly equal to taking the marginal PMF of the discrete random variable and multiplying it by the conditional PDF of the continuous random variable given the discrete random variable. If you don't remember this, we have a proof in a separate video on discrete and continuous random variables, so go take a look. But essentially what you get is, again, like a version is the word I was looking for before, of Bayes' rule, where now we can compute the probability of woman or the probability of man given height using the information that we actually have and have estimated from the data. Because this we have, right? We know the probability of woman, it's approximately 1/3. We know the conditional PDF of height given woman. We have modeled this as a Gaussian random variable, and we know the parameters. We have estimated them from the data. And maybe that is this orange term here. And finally, this pink term in the denominator, this is the Gaussian mixture model, right? We have seen that we can obtain it by, maybe I have it here, yes, combining, again, the PMF of women times the conditional PDF given women plus the PMF of man times the conditional PDF of man. So now we just compute this and we get our estimate of the probability of woman given height. When we plug in everything we have, so notice that here we're plugging in the Gaussian, it's actually there like that, the Gaussian PDF weighted by the different probabilities of women and men. It's actually very useful, to realize that this term is exactly the same as this term. So we can divide everything by that and get an expression where we have a 1 in the numerator, this other 1 in the denominator. And here we have a term where whatever we have within the exponentials get summed, and what was outside the exponentials get multiplied. And at the end of the day, when we take a look at, when we plug in all of the numbers here, we get this expression where there's a 1 here, and there's an exponential of the feature. And this might remind you of a logistic function, which is actually often used for classification using a different technique called logistic regression, which we will talk about in a separate video. But it's not exactly the same because we have this term here. However, if the variances of the two Gaussian distributions were the same, then that term would cancel out and you would get something that is actually a logistic function. So this is a way of justifying why we use logistic functions for classification. But again, that's a different model that we will talk about in a separate video. Okay, so this is our expression. This is our expression for the probability of woman given height. Let's take a look at what happens if we actually visualize it in a graph. It makes a lot of sense, okay? The probability of woman is almost 1 when the height is small. It's almost 0 when the height value is very large, which makes a lot of sense because, as we've seen in the data, women tend to be shorter than men. I've also here we've also visualized the probability of man given height, and which is just 1 minus the probability of women given height. It makes a lot of sense. It does have kind of like a logistic shape, but it's not exactly a logistic function. Okay, and then we can just apply this to classify new data points. How do we do that? Well, if someone's height is 180, then they're probably going to be a man. If someone's height is 160, they're probably going to be a woman. If someone's height is, I don't know, 166, then we're not sure. Okay. So that's basically what I've just explained, which is fitting a Gaussian model to each of the classes and then applying Bayes' rule. That's Gaussian discriminant analysis. So the idea is that we use a Gaussian mixture model for classification. We first estimate the conditional PDF of the features given the class using a parametric model. And this is necessary when you have more than, 5, 10 features. Okay, and in that regime, non-parametric models are not going to work well due to the curse of dimensionality. So that's why we're using a Gaussian random vector. I do want to emphasize that point. And then for each class Y, we fit the Gaussian to the training examples by estimating the mean parameter and the covariance matrix parameter. We're also going to need to estimate the PMF of the classes, which is very easy. We just look at the fraction of data examples that belong to each of the classes. Then we classify the test data based on the conditional probability of each of the classes given the observed features, which we obtain applying Bayes' rule. Okay, notice that the number of parameters that we have to estimate scales quadratically with the number of features. Why is that? That's because we have to estimate the covariance matrix of each of the Gaussian parametric models, and the number of entries in the covariance matrix is d squared, where d is the number of features. Okay, so let's take a look at an example where we apply this to diagnose Alzheimer's using MRI scans. Again, what happens in Alzheimer's? When we have cognitively normal patients and we compare their MRIs to Alzheimer's patients, what we realize is that basically the brain regions shrink so that this space here, like this, it's most obvious here, like the ventricles expand because all of these regions here, or well, some of these regions here, I guess, have shrunk. So motivated by that, we're going to use two features, which are the volumes of important brain regions that are typically associated with Alzheimer's. One of them is the hippocampus, which probably you have heard of, and the other is the entorhinal cortex, which probably you have not heard of, or at least I hadn't heard of. Okay, and here is our training data, which is extracted from the Alzheimer's Disease Neuroimaging Initiative. And what we see is that basically, if you look at the Alzheimer's patients, which are represented here as black dots, they do tend to have smaller volumes of the hippocampus and the entorhinal cortex, whereas the healthy patients have larger volumes in general. It's important to mention that here the volumes are normalized because some people, like myself, have very big heads, and you want to correct for that. So there's some pre-processing that is needed. Oh, and also the volumes have been estimated from the magnetic resonance imaging scans using basically a segmentation tool that determines what pixels belong to each of the brain regions and then essentially counts the voxels. It's voxels because it's 3D pixels. They're 3D magnetic resonance imaging scans. Okay, so now we want to apply Gaussian discriminant analysis to perform classification based on this data. So what do? First, we fit Gaussian models to each of the two classes. So here in gray, you see the one for Alzheimer's, and in black, you see these are the contour lines. So the lines on which the conditional density is constant. You see it for the hippocampus. So this point here is the mean of the conditional distribution of the Alzheimer's patients, and it's obtained by just averaging the volumes for all of the Alzheimer's patients. The mean of the healthy patients is obtained in exactly the same way, but then we averaging the healthy patients instead. And the covariance matrix parameter, which is obtained with the maximum likelihood estimate that we discussed before, determines the shape of these lines here. So the variance that the healthy patients I just shown and the Alzheimer's patients have in different directions. Okay, so we do that with the data that we have, and we can do it because we know which are the Alzheimer's patients and which are the healthy patients. And then we compute the conditional PMF of the class given the features. This is exactly the same as what we did for height, except that here I'm writing it more generally with C classes. We apply Bayes' rule, where we basically use the fact that the chain rule between discrete and continuous random variables hold, so that we can write the conditional PMF as the marginal PMF times the conditional PDF divided by the marginal PDF. And now we have everything here, right? Because we know the fraction of data corresponding to each of the classes, and that gives us the marginal PMF of the class. These guys are all Gaussians with parameters that are, again, estimated from the data, as I just showed you. So we can plug in the Gaussian PDF here and compute the probability of the class given the features, exactly like as we did in the case of height, except that the formulas here are more complicated because we have these Gaussian covariance matrix parameters as opposed to just the variance or the standard deviation parameter, as in the case of the height example, because there we only had one feature. This is what the probabilities look like for our example. Along this line, the probability of Alzheimer's is 0.01. Along this line, it's 0.1, 0.25, 0.5, and 0.75. So it makes a lot of sense, right? The smaller the entorhinal cortex and the hippocampus, the higher the probability of Alzheimer's. Imagine that we diagnose Alzheimer's if the probability is larger than 0.5. This is the best way of, this is the way of minimizing the probability of error according to the model. Notice that this is probably not what you want to do if you're doing medical diagnosis, because in that case, you probably don't want to have false negatives, especially if you're dealing with perhaps other illnesses such as cancer, but also in the case of Alzheimer's, you don't want to miss Alzheimer's cases. You care more about that than perhaps about having some false positives. And we will talk about how to evaluate classification models in a separate video using Alzheimer's as an example. But for now, let's imagine that we just diagnose Alzheimer's if the probability is above 0.5. In that case, our error rate on the training data is 24.2%, which is not too bad. We should compare to some kind of baseline. You should always find some reasonable baseline to compare to. The baseline that we're going to use here is just saying that everyone is healthy, because there are more healthy individuals than Alzheimer's patients. If you do that, your errors are 27.1%. So, the model is doing something. We have a 3% reduction in error from the naive baseline. However, you should be very bothered about what I just did. And I would encourage you to stop the video for a moment and think why you should be very bothered about this evaluation. Okay, so the reason why you should be very bothered is because I'm evaluating on the same data that I used to train the model. This is not a huge deal in this case because we only have two features and we have a lot of data. So the model is going to find it very difficult, and then we have a pretty simple model. So the model is not going to be able to overfit too much, but it's definitely a no-no in practice. You should never do this. You should always evaluate your models on completely held out data that have not been seen while fitting the model. So in order to do that, we apply our model to a different data set, which is from the National Alzheimer's Coordinating Center. And if you look at the data, so here the probabilities are going to remain the same, but the data is going to change. Actually, the distribution of the data is a little bit different. And this will often happen when you try to deploy classification models. You might have some differences in distribution, and it's very important to understand whether your models are robust to them or not. So let's evaluate our model on this test set. What we find is that if we again diagnose when the probability of Alzheimer's is above 0.5, not a great idea in practice, but we're going to go with it. And again, there's going to be a video on evaluating classification models that you can take a look at. Here, the error rate is 18.5%. So it seems that our model is working better. But when we compare to the baseline, actually the model is working in a very similar way. It's just that here, this data set is a bit easier in terms of overall errors because there are less Alzheimer's patients. So if we compare to the naive baseline where we just say everyone is healthy, the error goes down from 21.6% to 18.5%. Again, a decrease of 3%, just like we had in the training set, which indicates that we had not overfit the training set. But still, this is super important. You should always evaluate on held out data. Okay, so let's take a closer look at the model that we have just fitted. This decision boundary is basically the lines where these probabilities are constant look very nice. Okay, why do they look so nice? They look so nice because they're quadratic functions. Let's see why that is the case. Okay, now my lines are not quadratic, but the lines underneath are. So, okay, this looks a little bit daunting, but let's parse it. Remember that, what do we have here? This is the conditional PDF given the class Y. Okay, we multiplied by the marginal, and down here we have the marginal PDF, which is composed by all of these conditionals multiplied by the corresponding marginal. Now we're interested in these boundary surfaces where if you look at the ratio between the probability of two classes, the ratio is constant. Let's set it to 1 just for simplicity. That's what happens. That's what is often called a decision boundary, because here on one side of the boundary, the probability of A is going to be higher, and on the other side of the boundary, the probability of B is going to be higher. In our example, that would be specifically the boundary that I'm actually referring to, just to be clear, is this guy, 0.5, right? On one side, the probability of healthy is higher. On the other side, the probability of Alzheimer's is higher. So we're going to try to see why that has that shape. So we're basically going to write this expression plugging in A and plugging in B. But if you realize, the denominator is exactly the same for both. It's just the marginal of the features, which doesn't change, right? Like here, the features are the same. So because of that, they're going to cancel out when we divide them. Because here we're dividing. Notice that here we're dividing. So the denominators are just going to cancel out. And we're going to end up with this formula where we have 1 equal to all of this thing. Again, it looks a little bit scary, but it's not going to be so difficult to analyze. What are we going to do? We're going to take logarithms. We're going to take a logarithm here on both sides because we have that exponential. When we take the logarithm of 1, we get 0 on the left. And on the right, we get the logarithm of this stuff, which doesn't matter because it's not a function of the features. So we can just ignore it. And then we have this expression here, which is a function of the features, where essentially we have these terms where we're multiplying the inverse of the covariance matrices by x minus the mean on one side and x minus the mean on the other side. If you compute that out, what are we going to get? We're going to get terms where the entries of x are going to be either multiplying another entry of x, or multiplying themselves, or multiplying some entry of mu. So basically, we're going to have a polynomial of second order, a second order polynomial. We're going to have like squared of the first entry of x times some number plus the first entry of x times the second entry of x by some number, and so on and so forth. So that's basically going to be a quadratic function. And that's why we observe quadratic boundaries such as this one. Wow, like today I can draw a line. There we go. Okay. But what if you wanted a linear decision boundary? In some cases, this would enable you to overfit a little bit less because maybe the quadratic boundary could overfit in some instances. In that case, if you look at this very closely, the part that is really quadratic when you expand all of this out, okay, is actually this one, where you have x on the left and on the right, and x on the left and on the right. And then they're multiplying the corresponding inverses of the covariance matrix parameters of the conditional distributions of the two classes. But what happens? There's a minus here if you compute things out, which means that if the covariance matrix corresponding to the two classes are the same, then boom, things cancel out, and you get a linear model, because basically this disappears and you get all the rest, which is just like an affine function of x. So you're going to have linear boundaries. And that's exactly what happens. Maybe I should have shown you directly, but so again, just recapping, we have our training data. If we fit the two Gaussian distributions separately to each class, and then we compute the conditional probability of Alzheimer's or healthy given the features, we get this quadratic function. But if we constrain the covariance matrix to be the same, then we're going to get a linear boundary that looks like that. Okay, so this is what I'm saying. Now let's go back for a moment just to make sure that we understand what I mean by the sample covariance matrix being the same. So here, I hope it's clear what we do to compute the sample covariance matrices. First, we compute the two means. We subtract the corresponding mean for every data point, and then separately for the healthy patients and for the Alzheimer's patients, we compute the sample covariance matrix using the maximum likelihood estimate. Okay, and that gives us those two covariance matrices. Here, when we want to constrain the covariance matrices to be the same, I encourage you to stop for a moment, stop the video, and try to think how you would do it. Because it's, not completely obvious, but it's an interesting exercise. So I encourage you to do that. Okay, and now I will tell you how we do it. So imagine that you have the data points that have Alzheimer's here, and the data points, well, maybe another color. Maybe I'll go for blue. The data points of the people that are healthy here. What you do is the following. You use, let's draw some axes over here. Wow, amazing. I can't even draw straight lines with the tool for drawing straight lines. So basically what you do is the following. You take the Alzheimer's patients and you use their sample mean to center them. Whoop. Okay, and now you have them all here. And then you take, I like this circle here. Let's see if I can reproduce it. You take sorry, did I say the Alzheimer's patients? Those were the healthy patients, right? Now you take the Alzheimer's patients. So we have centered the healthy patients, and you take the Alzheimer's patients and use their sample mean to center. Okay, and now you use all of this data to compute the covariance matrix, which is then going to be centered at the corresponding sample means. This actually might be beneficial for one of the classes you don't have a lot of data. Okay, then the estimate for the covariance matrix will be less noisy. And the other advantage is that you have this straight boundary decision lines because of the fact that the quadratic terms, as we've seen, cancel out when we do the ratio between the conditional probabilities of the two different classes. And that's called linear discriminant analysis. I don't like this color, you can barely see it. Linear discriminant analysis as opposed to quadratic discriminant analysis, which is the general Gaussian discriminant analysis that we obtain when the covariance matrices are different. How does linear discriminant analysis do in our case? Very similar. So the training error is almost the same. Compared to the fraction of Alzheimer's patients, we get a reduction of 3%. That's the training error. That's not what's important when we're evaluating the model. What's important is the test error on this completely held out data set. And there we see essentially that it's exactly the same as the quadratic discriminant analysis. And again, we get a reduction of 3% from this naive baseline that just says that everyone is healthy. So maybe, as an exercise, you can think of how you would improve the model. Take a look at the data. And the solution, maybe if you want to stop the video, the solution is that you cannot really do magic here in terms of improving the model. The problem here are the data. You just need more features. As you can see, there's this overlap between healthy individuals and Alzheimer's patients there. You cannot do magic. Okay, if you actually discriminate within there, all you're going to do is overfit your training set. In this case, you just need more features. Okay, so what have we learned? We have learned what Gaussian discriminant analysis is, which in a nutshell is how to use Gaussian mixture models to overcome the curse of dimensionality and perform classification. And we have applied it to Alzheimer's diagnosis from features that were extracted from magnetic resonance imaging scans. And that's all I got. Thank you very much.